Hello, today I will talk about how to calculate the electrical flux of a 3D non-uniform electric field through a limited defined 2D plane. And this sounds difficult because of the rough wording, but it's actually pretty easy. So what the question is asking is if we have a non-uniform electric field and a two-dimensional plane, what is the electric flux of that field through that plane? Okay, so we are given a vector notation equation for the electric field, and that is as follows, and I'm just going to make the numbers up because it doesn't matter. So in fact I'll just use constants. So the electric field, when broken up into vector notation, the total electric field is going to be equal to a constant A times the y direction, comma, constant B times the z direction, and the constant C times the x direction. And you can see, because it has these three variables, that it changes the quantity or the magnitude of the electric field changes depending on which point you are at, which makes it non-uniform. And information about the plane we're given is that the plane goes from, I'll just make up numbers for this, x equals 0 to 100 centimeters, and then y equals 0 to 100 centimeters. So if we were to draw the plane on our 3D graph right here, we'd see something like this. It'd be a perfect square. And it would be completely flat in the xy direction. It would not go up or down at all. So this is our plane, and the purpose of using using the electric field as an example is that it's really easy to use something called Gauss's law to help determine what this electric flux is. So the equation that we're given, and you can prove this, is that the flux due to the electric field, which is just the symbol again. Oh, that's a terrible symbol. Slightly less terrible. So the flux due to the electric field is equal to the double surface integral over a set area of the electric field dot product with a dA vector. And that also equals the sum of enclosed charges, so any charges within that plane, divided by this constant 8.854 times 10 to the negative 12, I believe. And that's permittivity of free space. And by the way, that constant is equal to 1 over, well, let's see, k equals 1 over 4 pi times that constant. So that constant would be 1 over 4 pi k. So they just, physicists use that constant to avoid having pi in many of their equations, which I kind of see as pointless, but it's okay. So one important thing to notice about this equation that we need to use is that the E field vector is dotted with the infinitely small dA vector. And what that tells us is that we need to select the component of our E field vector that is normal to the plane, meaning perpendicular. So if we look at our 3D graph, any vector in the y-axis, or the y dimension, let's say this vector along the y-axis, that vector is parallel, so we can't have this one. Any vector in the x direction is also parallel, so we can't have that one. However, if we use the z direction, you'll see that every time, as long as the vector is parallel to the z-axis, that vector is normal or perpendicular to the plane. So that what that tells us is we need to use this component only for our E field. So what we can do now is plug this component in as our E field for this equation, because it's the only one that's perpendicular to the plane. And we get this equals still the double surface integral time of the constant c times the x direction times dA, which still equals all of this. I'll just stop writing the word enclosed because it really doesn't matter. So now that we have this, we can break up dA into components for the integral. So dA is the area, so we are dealing with a rectangular plane right here, or a square plane. So the area of a square is just x direction times the y direction. So dA becomes dx times dy. And now for our limits for the integral, we need to define how far into the x direction we're going and how far into the y direction we're going. So if this is the integral for x, because we'll have dx before dy, this would go from 0 to 100, and that's coming from here. So at this point, we're at 100 centimeters in the x direction, and then at this point, we're at 100 centimeters in the y direction. So then this would become 0 to 100, except one thing. We need to convert the centimeters into meters. So that would just be 0.1 meters and 0.1 meters. So make sure to convert the unit. So now if we simplify this integral and pull the constant out in front, we see that now we have the constant c, which is just any number that they give you, times the integral from 0 to y equals 0.1, and then the integral of 0 to x equals 0.1. That's the same thing as this, times x from our component of the vector, and then instead of dA we have dx dy, and that still equals this, which we will use later. So now we have two integrals to do. You do inner first, and then you can do outer second. In this case, you can actually do it in either order. It doesn't matter, but what you should do is, do this one first. So this one is going to be x squared over 2 raised from 0 to x equals 0.1. And that's just going to be 0.1 squared over 2, which equals 0.05, I believe. So now if we do the second integral, we see that c times 0, our integral from 0 to y equals 0.1 of 0.05 dy is just going to be equal to c times 0.05 times 0.1, which is just c times 0.005. Okay, so that is actually our answer for flux, and if they gave you a value for c, you just plug it right here. And if you did have a value for c, and you were to find what flux is as just a number, as a measurement, you'd be able to set this equal to, I'll still write it the way we have it because we don't have a number, c times 0.005 is still going to be equal to the sum of enclosed charges divided by that constant, 8.854 times 10 to the negative 12. So you know that number, that's just a number, and if you know this, you can now find what the charge in this plane is. And now this plane looks like a Pop-Tart. So thank you for watching.